Before you leave today, I will hand back your test from Unit 2. If you are eligible to do test corrections, I've attached the sheet. I'll go over with you again before we leave about how to do those, since many more of you are eligible this time. All right, let me come around and check page 16. You also need out pens or pencils and calculators. If you could make a note of what the assignments are up on the screen now before we get going. Okay, so as we go over this homework, I want you to realize that my answer may, or your answer and mine, if we differ on what they are, that may be acceptable, right? Because it's more the method of how we're doing this that's important, not the exact final answer, because we all had to draw lines. And if our lines aren't like photocopies of one another, and we didn't choose the same 2 points to use in our slope calculations, we may not necessarily have the exact same answer. And that is okay, so long as the process that you worked through and the physics knowledge is all correct. Do you understand what I'm saying? Okay, so let me go through what I did for each of these three. So in questions 4 and 5, we asked you for an average velocity, which meant you had to draw secant lines connecting the 2 time points given. So double check in number 4 from 0 to 2 seconds. This is my secant line connecting here and here. That's this blue line right there. That's my secant line I used in number 4. And then in number 5, we were asked to do it between 4 and 6 seconds. So if I look at 4 seconds on the parabola and 6 seconds on the parabola, they're there. I then drew my secant line connecting those two. So my red line on this picture was my secant line. You should have those 2 lines drawn correctly. Then you're going to find 2 points on each line. So I'm going to start with number 4. I chose those 2 points at 0 and 2 seconds using the same precision from the graphs, which means at 0 seconds, I was at 0.0 meters, and 2 seconds, I was at negative 4.0 meters. I'm looking for the average velocity, so the V bar. I'm going to do it using my slope equation. V bar is y2 minus y1 over x2 minus x1. I'm plugging in the coordinates of both points, including their units on both sets of numbers. I then do my intermediate subtraction. I see I have 2 sig figs in the top, 2 sig figs in the bottom. So my final answer with 2 sig figs would be negative 2.0 meters per second. And we always divide it out, getting an answer as a decimal with sig figs. We don't leave things as fractions in this class. All right, any questions on 4? All right, and number 5, again, I used the same points, which were the 4 and 6 second time points. So at 4.0 seconds, I had negative 16.0 meters. At 6 seconds, it was negative 36.0 meters. Again, I'm looking for V bar. So V bar is y2 minus y1 over x2 minus x1. I'm then plugging in both of those coordinates with their units. I do my intermediate subtraction, which shows me 3 sig figs in the top and 2 sig figs in the bottom. So I'm going to round to 2 sig figs, which gives me negative 10 meters per second. So you should have something very close to that. Maybe your sig figs are different because the coordinates you chose were different. All right, and lastly, number 6, I want the velocity at 8.0 seconds. This is an instantaneous velocity, which means you needed to draw a tangent line at the 8-second time point. So if I find 8 seconds on my graph, here's 8 seconds, I come up, there it is. I did my 2 little marks on either side of that point, and I drew in my green tangent line. So your tangent line should look something similar to what I have there. Does it? Something similar to that. It doesn't go back to the origin. Okay, it should be, and it should not cross the parabola either. That's the other thing. If your tangent line crosses the parabola, goes from one side to the other, that's wrong too. Okay, Now, find 2 points. I used this point and that point in my calculation because there were grid lines intersect. You can see that. So my coordinates, which are probably different than yours, are 3.0 seconds and 20.0 meters and 9.0 seconds and negative 80.0 meters. I'm looking for V with the arrow, the velocity, not a V bar. V bar is average velocity. So V with the arrow is y2 minus y1 over x2 minus x1. I'm now going to plug in. So negative 80.0 meters minus 20.0 meters over 9.0 seconds minus 3.0 seconds. So in the numerator, I have negative 100.0 meters because I have to keep the precision. So 4 sig figs in the top. And in the denominator, I have 2 sig figs because of 6.0 seconds, keeping the precision. So I'm going to round, bless you, to 2 sig figs, which gives me an answer of negative 17 meters per second. So you should be somewhere close to that. Like negative 40 meters per second would be wrong. Likewise, negative 2 meters per second would be wrong. That's telling me for sure that your tangent line is drawn incorrectly or you didn't read the coordinates of those points correctly. I have to check all of that when you do it. Any questions on that page? Basically, a review of what we spent the last 2 days doing. We're good? Okay, so for today's quiz, it is a Google Classroom quiz. So what I'd like you to do is keep this out so you have some place to do some scratch work. Keep out pens or pencils and calculators so you have the opportunity to do your work in the question. Let's now go on to our Google Classroom page. And let's find our quiz here for Unit 3C today. Go ahead and take this quiz now. Again, you'll need scrap paper to do it. So if you have the homework out in front of you, you can use that to help you, okay? Good luck. 3 quick questions on this. And once you've finished, you can put the Chromebook away. And we're also going to need our notebook and our reference table. All right. Today we're going to start section D of Unit 3, which is our second to last section. We'll only have one more section after this. It will take us 2 class periods to get through the notes and practice questions I have in the packet. So today and 1 period tomorrow. Please make sure you bring a fully charged Chromebook with you to class tomorrow, because we are going to start another lab in class tomorrow after we finish working on some practice problems associated with this. And notice that what we're looking at today is kind of the counterpart to what we were doing the past couple of days with position time graphs. So now, instead of having a position time graph, we're going to have a velocity time graph for an object that's accelerating. And we're going to ask you to do some calculations to determine some specific things about the object's motion from the velocity time graph. And we are going to add an equation to our reference table on page 6. So make sure you have your reference table out in front of you, opened to page 6, because we'll be using that in a minute. So here's what you'll be quizzed on what is today? Tuesday, so Thursday. You'll be asked to do 3 different types of calculations for a velocity time graph. We could ask you to calculate the object's acceleration from their velocity time graph. We could ask you to calculate the object's average velocity from the velocity time graph. And then we could ask you to calculate the object's displacement from the velocity time graph. Those are the 3 calculations we're going to learn how to do from our velocity time graph. So let's do a little review, because some of these we've already learned how to do. Remember that velocity on our graph will be on the vertical axis, and it is our dependent variable. That is review from what we learned, back at the beginning of Unit 2. Time, of course, since it's second in the title, indicates it's going to be on the horizontal axis of our graph. It is our independent variable. And we learned previously in this unit that the slope of the line, these are all lines, either horizontal if we have a constant velocity, or diagonal if it's accelerating, that the slope of that line is the object's acceleration. Do you know how to find the slope of a line? Gosh, I hope so. We've only been practicing slope calculations for a couple of weeks now in this course. So let's talk about what that means. It means that slope equation that we learned or reviewed in Unit 1 is going to come back again now for the lines. What's nice is you're already going to have the line. You don't have to draw in a line. You've already got it. You just got to find 2 points on the line and plug them in to that equation and solve. So it means that if you calculate a slope on the velocity time graph and you get an answer of positive 2 meters per second, or meter per second squared, that means that the object's acceleration was directed to the right at 2 meters per second squared. The positive means it was accelerating to the right. If the slope was negative 6 meters per second, that's telling you that the object's acceleration was directed to the left, and the magnitude of that acceleration was 6 meters per second squared. Likewise, if you get a slope of 0 meters per second, it tells you that the object was not accelerating, and the velocity was therefore constant. Whatever the velocity value was did not change over the time period you're looking at, which means you either had a constant velocity or it wasn't moving. Either one. Okay, and what shape would you get for that? A horizontal line. A horizontal line on a velocity time graph means you're not accelerating. You have a constant velocity. Okay, so that is kind of a review of what we've talked about previously. I'm not going to go through how do you do a slope calculation. We've only been practicing that now for a couple of weeks. We should be good with that. Show me your givens are your 2 points with their coordinates. Show me your unknown is A. Show me the equation that A would equal change in Y over change in X, or Y2 minus Y1 over X2 minus X1. You follow what I'm saying? Yes? Okay. So let's look at the new stuff then. Let's now talk about how you get an average velocity from these graphs. So you can see on this particular velocity time graph, the object is speeding up as it moves to the right. And it starts off with a velocity of 0 meters per second, which we can see right here. 0 meters per second as our y-intercept. And at 5 seconds, its velocity is now positive 50 meters per second. This equation for average velocity is not on your reference table, and I'd like you to add it. Let me show you how to add it to your reference table, okay? So on your reference table, we have this equation right now for average velocity, V bar, right? Isn't V bar average velocity? Is d over t. That still works, but we don't have the displacement from the graph. Not yet. Instead, what we can do is we can also get V bar by now taking the initial velocity and adding it to the final velocity and dividing by 2. It's like if you'd had 2 tests this marking period, and I want your average test grade, what would I do with your test grades? You took 2 tests. Add up, divide by 2. That's what you're doing here. You've got 2 velocities, which you're reading off the graph, the start and end point of the line segment. Read those velocities off the graph, add them up, divide by 2. That's what you do to get your average. This is why it's not given to you on the reference table, because we assume that by the time you get to 11th and 12th grade, you know how to find averages of data. You add up the data points and divide by the number of data points. That's exactly what you're doing here. You're getting an initial and a final velocity from your graph by reading this value as your initial velocity. That value is your final velocity. So 0 plus 50, that's 50. I divide it in half. So my average velocity would be positive 25 meters per second, which also happens to coincide to the velocity at the middle time. If I were to read the graph at the middle time, 2.5 seconds, I would get the same velocity by just reading the graph. That only works for a single line segment. So if this graph were diagonal and then went horizontal at 5 seconds and beyond, I couldn't do it for the entire graph. I can only do it for one segment at a time. Now, on that graph, therefore, the average velocity, as I just showed you, would be positive 25 meters per second. Does that make sense, everyone? Okay, so then let's look at the last calculation you'd have to know how to do, which is a displacement calculation. Taking the equation that we learned in Unit 2, velocity is displacement over time. We're now going to use the bar over the v because our velocities are not constant anymore. Average velocity is displacement over time. So if I move that around for the displacement, I take the average velocity and I multiply it by the time. Right? Didn't we see this in your last unit? It was the same thing. We said what we're going to do, if I have a velocity is a displacement over a time, to get the displacement, I just multiply both sides by the t. It's the same equation we saw last unit, except we're being more specific about what type of velocity it is that you're finding, because our velocities aren't constant anymore. It's an average velocity that you're finding. Okay? So once you know your average velocity, you can get your displacement by multiplying the average velocity by the time. And the other way we said we can do it is by calculating an area. Remember we talked about shading in our graph between the velocity line and the time axis. And that area that we shade in is the displacement during the time interval. So if you prefer to find an area instead of using the kinematics equation, that's okay as well. They are equivalent. They are equivalent. So that would mean, though, if you want to use the area method, that the method you're going to use or the equation you use to find the area depends on what shape the area is. And I want to show you an example of a couple different shapes that you might see. Okay? I've got one more slide. And that's showing you how we can see the areas as different shapes and where you might find that on your reference table to help you. Is everybody set with this page, this slide? Okay, so let's take a look. On our reference table, can you find this section? It's on the previous page, page 5. The two area formulas that you will be using if you want to use an area method are this one here for rectangles. So you can check off that equation for the area of a rectangle, base times height. And then you also have this one here for a triangle. That's the other one that we'll be using. Area is half the base times the height. Check those two off on page 5 under geometry and trigonometry. So from your reference table, let's say, for example, this is showing an object slowing down as it travels to the right. It starts off at positive 40 meters per second and ends up at 0 meters per second over that 4-second time interval. So when I shade in that graph between the velocity line and the time axis, I end up getting a triangle. So that triangular area would represent the displacement between 0 and 4 seconds. So if I asked you to calculate the displacement, you could just calculate the area of that triangle if you'd prefer, instead of using that equation. So I would do half of 4 seconds times the positive 40 meters per second, which would give me positive 80 meters. I would get the same answer this way because the average velocity is the average of 40 and 0. What's the average of 40 and 0? 20. So 20 times 4 is 80. I get the same answer. Either way, it gives you the same answer. The method you prefer to use is up to you. Okay. Likewise, I might see something like this. This shaded area, notice it's not starting at 0 seconds. I'm starting at 1 second. That area is the displacement from 1 to 3 seconds on my velocity time graph. And that's a trapezoid. What we do whenever we have a trapezoid is we break it down into rectangles and triangles. Can you see where the triangle is at the top and the rectangle at the bottom? If I break it up, what could I then do with those two areas to get the displacement? Add them up. That's exactly right. And the reason we do that is because I don't have the trapezoid area equation on my reference table. I only have the triangle and rectangle. So that shaded area would represent the displacement from 1 to 3 seconds. So I would start off by finding the area of the triangle. I'd add it to the area of the rectangle. And that would give me positive 40 meters. If I chose to do it this way, though, I would look first for the average velocity from 1 to 3 seconds. Notice at 1 second, the velocity is positive 10 meters per second. And at 3 seconds, the velocity is positive 30 meters per second. What's the average of positive 10 and positive 30? Average of 10 and 30. Add them up, positive 20. So if I did it this way, I would just take positive 20 meters per second and multiply it by the amount of time between 2 seconds. What does that give me? Positive 40 meters. Isn't that the same answer we get by combining the two areas? So the method you choose to use is up to you. Okay? Questions? All right, let's practice this then. In your packet, turn to page 17. Oh, I have a summary here. How do you get acceleration? Find the slope. How do you get an average velocity? Add them up, divide by 2. Add your 2 y coordinates, divide by 2. How do you get the displacement? You either find the area or you take the average velocity and multiply by time using this equation from your reference table. Okay? All right, now we'll go to the packet. Page 17. Shoot. All right. Question 1. What does the slope of a velocity time graph represent? Yes, it represents the object's acceleration. All right, so now in number 2, I want you to find the acceleration during each of the time intervals. So starting with 0 to 5 seconds, we're going to find 2 time points, and let's list the coordinates of those 2 times. 0.1 would be 0 seconds, and 0, look at the units, those are meters per second. 0.2 is at 5 seconds, and that would be 10 meters per second. Those are to the ones place, so 10 meters per second. The unknown is acceleration, which is a lowercase a. So we're going to use our slope formula for that. A is y2 minus y1 over x2 minus x1. We're now going to do our substitution with units. Oh, and by the way, that is a velocity, so it should be positive 10 meters per second. You know, when you make a graph in Google Sheets, the positive numbers, it never puts positive signs in front of it. You just can't make it do it. I don't know why, it just won't let me. So positive 10 meters per second minus 0 meters per second all over 5 seconds minus 0 seconds. So that is positive 10 meters per second over 5 seconds after I do the intermediate subtraction. I don't think you need a calculator to get that answer. What does that mean the acceleration of this object is? Do you know? Yes, or 2 meters per second squared to the right. 1 sig fig. Okay, let's now look at 5 to 15 seconds. So there's 5 seconds. There's my 15-second time point. Let's list our givens again. 0.1 and 0.2. 0.1 was at 5 seconds and positive 10 meters per second. 0.2 is at 15 seconds and positive 10 meters per second. The unknown is acceleration. How do we find acceleration? Use your slope. So the acceleration is y2 minus y1 over x2 minus x1. So the acceleration is positive 10 meters per second minus positive 10 meters per second all over 15 seconds minus 5 seconds. So the numerator is 0 meters per second, and the denominator is 10 seconds because we keep precision when we subtract. What does that mean this acceleration is? 0 meter per second squared. We still want a unit on it, meters per second squared. It wasn't accelerating there. In other words, the velocity was constant. Weren't those velocities constant? 10 and 10 didn't change. All right, how about you try 15 and 20 seconds right now on your own? Show your work. Do it between 15 and 20 seconds. Remember, you can't leave answers as fractions. You have to divide through getting answers with proper units, sig figs, and direction. Give you another minute to wrap up question C. All right, let's check your work. In section C, 0.1 is 15 seconds and positive 10 meters per second. 0.2 is 20 seconds and positive 4 meters per second. I want the acceleration A. The equation is A is y2 minus y1 over x2 minus x1. So my substitution, A is positive 4 meters per second minus positive 10 meters per second, all over 20 seconds minus 15 seconds. So the numerator is negative 6 meters per second, and the denominator is 5 seconds, 1 sig fig. So my answer gets rounded to negative 1 meter per second squared. Questions? Kim?
Just double checking. If you just write A equals change in Y over change.
That's fine.
Okay.
That's fine. All right, let's try part D, 30 and 40 seconds. Olivia, can you tell me the coordinates of the first point, which is at 30 seconds? Good. Kari, can you tell me the coordinates of the second point, which would be at 40 seconds? And 0 what? Good, 0 meters per second. What's the unknown letter, Brandon? Yep. Josh, what equation should I use to calculate A? Yes. Let's do our substitution with units. So 0 meters per second minus positive 4 meters per second, all over 40 seconds minus 30 seconds. So that's negative 4 meters per second, all over 10 seconds. So Fig, can you tell me what that's going to give me for the acceleration? Okay, so you got to make a decimal. Good, negative 0.4 meters per second squared, because we need sig figs. Fractions don't have sig figs. We have to have it with sig figs. 1 sig fig in the top, 2 in the bottom, so we round it to 1 sig fig, negative 0.4 meters per second squared. Any questions on page 17? Acceleration question should be a piece of cake, if you remember how to get it, that it is a slope. All right, let's go to page 18. Now on page 18, we want to calculate accelerations in these time intervals from 0 to 1 second, 1 to 4 seconds, and 4 to 12 seconds. Actually, let's skip this page for now. Skip it for now. And let's skip it on page 19 also. We'll come back. They're all the same. Same questions on all three. Yes, let's look at page 20. This one's giving you a velocity time graph. I want to know what is the average velocity during each of these time intervals. Oh, how do we get the average velocities? You remember what we have to do? You have your notes in front of you, right? Pia, can you tell me how we get an average velocity from a velocity time graph? Yes, initial plus final over 2. So what we're going to do, let's look at these times. These are not givens. The times are not givens. We use those to help us get the VI and the VF. The VI is at 0 seconds. So read the graph at 0 seconds. What is the velocity at 0 seconds? 0.0 meters per second. The final velocity is at the 1 second time. Do you see where 1 second is on the graph? Right here. What is the velocity at that time, Emily?
0 meters per second.
Yep, 0.0 meters per second. The unknown is the average velocity, the V bar. And he already told us how to get it. We're going to use V bar is VI plus VF over 2. So let's do our substitution. 0.0 meters per second plus 0.0 meters per second all over 2. What's 0 plus 0? 0. 0 divided by 2. So the average of 0 and 0 is 0.0 meters per second for that average velocity. You got a 0 on 2 quizzes, and I wanted the average of those 2. You still got a 0. All right, let's now go to the next time interval from 1 to 4 seconds. Cam, what's the VI for that time interval?
0.0 meters per second.
Good. Ashley, what is the VF for that time interval? And is it positive or negative? It is positive. So again, the unknown is the V bar. And the way we're going to get that is by adding up those velocities and then dividing by 2. So we're going to take 0.0 meters per second and add it to positive 3.0 meters per second and then divide by 2. The number 2 doesn't have sig figs, by the way. It's not a measurement. So if I add 0 to 3, you get 3. What's 3 divided by 2? 1.5. So we're going to keep the precision. So that means the average velocity is positive 1.5 meters per second. Make sure you're adding the velocities. The common mistake is that kids want to subtract them. And I'll tell you, if you start subtracting the velocities for an average velocity, I will start subtracting your test grades to calculate your average test grade in my class. So if you got 100 on one test and a 90 on the next test, what's the difference? 100 and a 90? That's 10. And then I would have to divide that by 2. So I would say your average in my class was a 5% instead of a 95%. So make sure you're adding your grades, not subtracting them. Adding the velocities, not subtracting them. That's the most common mistake I see, is that kids want to subtract them, and I don't know why. Okay, let's go to the next one. 4 to 5 seconds. Savannah, what's the initial velocity from 4 to 5 seconds? Yeah. Alex, what is the final velocity from 4 to 5 seconds? Good. And we want the average velocity, the V bar. So again, you're going to add them and then divide by 2. So Nick Rushford, can you tell me what that average is? Average of 3 and 3? Positive 3.0. Yeah, meters per second. The average of 3 and 3 is 3. All right, how about from 5 to 13 seconds? Nick Rennick, what's the initial velocity there? Yeah. Jules, what's the final velocity for that time interval? Good. The unknown is the average velocity, the V bar. So we're going to take the VI, add it to the VF, and divide by 2. So positive 3.0 meters per second plus negative 5.0 meters per second divided by 2. Positive 3 added to negative 5 is negative 2. Negative 2 divided by 2 is, okay, so keep it with the same precision. So we're going to say negative 1.0 meters per second for that time interval. Okay, let's now go 13 to 15 seconds. Caitlin, what's the VI for that time interval? Good. Addie, what's the VF for that time interval? Good. Again, we're looking for the V bar. So we're going to take VI, add it to VF, and divide by 2. All right, let's stop there because I want to hand back your tests. We'll pick up with more of this tomorrow. Just study tonight, please. Try to commit this kind of information to memory. If you have a test correction sheet attached, you are eligible for test corrections, which require a parent signature by next Tuesday. Please don't leave until I've handed this back to you. The back row now. When you go.